Okay, so apologies for the delay, everyone. And the next presentation will be from Emanuel Malvetti, who will talk about quantum circuits for sparse isometries. Please, Emanuel, take it away.
Thank you. So good afternoon from Zurich, and thank you for giving me the opportunity to speak here. The title of my talk is Quantum Circuits for Sparse Isometries, and there's a preprint on the archive with the same title if you are interested in the details. And there will also be some open source Mathematica code, which we will make available in the near future if you want to test out the methods that we implemented here. So this work came out of a semester project that I did at ETH, which was supervised by Raban Iten. And the paper was written together with Roger Colbeck from the University of York. So let's first recall some of the words that are used in the title. So you all know what a quantum circuit is. And here each horizontal line represents a qubit. And here we have one qubit that is in a fixed initial state. And the entire circuit can be represented by a unitary matrix. Now, since we have one input that is fixed, we can actually delete some of the columns of this unitary matrix without changing anything about the functionality of the circuit. And when we do this, the resulting matrix is called an isometry. So an isometry is just a matrix that has orthonormal columns, and then this will be an isometry from 3 to 4 qubits. And the goal of this talk is to show how you can go from an isometry to a quantum circuit. And in particular, we will be interested in sparse isometries, so isometries that have a lot of zeros. And the quantum circuits that we're going to implement are going to use single qubit gates and CNOT gates. And we will take the number of the CNOT gates in this circuit as the cost metric, which we're trying to minimize. So there are two special cases of isometries. For m equals n, we have a full unitary, and for m equals 0, so if all input qubits are fixed, we have essentially state preparation, and the isometry is just composed of a single column. And for the general case of isometries, there exist near-optimal decompositions, and they can be upper bounded by about 2 to the n plus m CNOT gates. And this is about twice the best known lower bound. So this means that in the general case, we cannot improve this by much, which is why we're going to look at sparse isometries instead. So here are some examples of sparse unitaries. For example, you have permutation gates. These represent classical reversible circuits. And using the method that we describe here, a variation of it, we can implement permutation gates on n qubits using at most 18 times n times 2 to the n CNOT gates. Another example are diagonal gates, which can be implemented using 2 to the n CNOT gates, and uniformly controlled single qubit gates, which apply a different single qubit gate depending on the state of the control qubits, can be implemented using 3/2 2 to the n CNOT gates. And in each case, you can see that the number of CNOT gates that is required to implement these isometries is more or less linear in the number of non-zero entries of these isometries, except here we have this factor of n. And so the goal will be to do kind of the same thing in the general case for arbitrary sparse isometries. And we will see that it is indeed possible to achieve similar counts. So first, the general approach to decomposing these isometries is as follows. We try to find a sequence of gates, so in our case, single qubit gates and CNOT gates, that we will apply to this isometry V, such that it will be reduced to the identity matrix, or more precisely, to the 2 to the m first columns of the identity. If we multiply this equation by G dagger, we will see that G dagger is an extension of the isometry V to a unitary matrix. And since we have a circuit for G dagger, we have a circuit for G, we can also find a circuit for G dagger, which will then implement V. And more precisely, we will proceed in a column by column fashion, where we will reduce each column at a time until we arrive at the identity gate, or more precisely, we will try to first arrive at a diagonal gate, and then we will fix these diagonal entries to obtain the identity. And so what is important here is that we try to preserve previously reduced columns, because these gates are effectively acting on all columns at the same time. And for sparse isometries, we also have to make sure that we preserve the sparsity so that we don't have too much fill-in. So as I said, sparse state preparation is simply an isometry that has a single column. So we should start there by trying to improve state preparation for sparse states. So if you have, for example, a state on n qubits, which has at most 2 to the s non-zero entries, so n and z stands for a number of non-zeros, then the approach that we take to do state preparation is the following. First, we try to permute the entries in such a way that all of the non-zero entries are grouped, or they are close together, such that they are effectively representing a state on s qubits only, and the other n minus s qubits will be disentangled and they will be in a basis state. And then we just have to do state preparation on s qubits, which is something that we know how to do. And the way to do this permutation is that we choose a set of s qubits and a set of n minus s qubits, and we will reshape the vector into a table where the rows correspond to the s qubits and the columns correspond to the n minus s qubits. And we will try to move all of the non-zero entries into a single column of this table. And we can do so by applying first n minus 1 CNOT gates, and then finally one S-controlled NOT gate to move it into the column. And if we do this, we get the following CNOT counts. So what is important here is that you have something that is proportional to n times the number of non-zero entries, which is what we were trying to achieve. What is also interesting here is that we can implement these gates up to relative phases, so up to diagonal gates. And it would be interesting to find decompositions of S-controlled NOT gates up to diagonal. These are currently just known for S equals 2, which is the Toffoli gate, and for S equals 3. So it might be interesting to find such decompositions for larger S. So now that we know how to implement a single column or to reduce a single column, we might hope to do this for each column one after another. However, this cannot really work, since if you reduce each column using this method, you will mess up the previously reduced columns. And the way to fix this is to use householder reflections. So a householder reflection is just a reflection with respect to a hyperplane that is perpendicular to some given vector, which we call W. And fortunately, we can write such a reflection in this way using state preparation, which we have already seen, and using a reflection gate R. And this gate simply flips the sign of the first component, which can be implemented using a fully controlled NOT gate and some single qubit gates. And in particular, if this vector W is sparse, then we can use sparse state preparation to implement this householder reflection. And a nice property of these reflections is, of course, that any vector that is orthogonal to W will not be changed. And this will help us in reducing the amount of fill-in that will occur. So using a sequence of householder reflections, we can then simply reduce one column of our isometry at a time. And this is just the usual householder QR decomposition. So this will then not mess up the previous columns. And yeah, this can be done for both sparse and dense isometries. And in the case of dense isometries, we get more or less the same nearly optimal synod counts that other methods also achieve. And interestingly, in the sparse case, we have some nice properties of these householder reflections that I'm going to show you. First, of course, if the isometry is sparse, then its columns are also sparse, and this means that this vector W, which we for which we have to implement sparse state preparation, will also be sparse. So this gives us some speed up or some improved synod counts for sparse isometries. And another nice property is that there will be reduced fill-in, which I'm going to show you on the next slide. Let's just look at the synod counts that we get from this decomposition. So here the important thing is that we have something that is proportional to n times this quantity elim, which is the number of eliminations that we have to perform during this decomposition. And this number can be larger than the initial number of non-zero elements of the matrix, since there might be fill-in. But I will also show you how you can find a bound on this quantity using matrix envelopes. So let's first look at the fill-in that we get from the householder reflection. If we perform one householder reflection to reduce the first column of some isometry, meaning that we are eliminating these two entries, one can show that all of the fill-in has to be, or can only occur in the columns that have a non-zero element in this first row. So here we have a non-zero element. This means that in this column we can have fill-in, but the fill-in can also only be in the rows in which this initial column has non-zero elements. So this means that the amount of fill-in is quite limited, and this also means that the number of eliminations is going to be relatively small, leading to relatively low synod counts. So one way to bound this number of eliminations that we have to perform is to use matrix envelopes. So this envelope can be represented by such a staircase line, which satisfies two conditions. It has to be below all of the non-zero elements. So below the envelope, there can be no non-zero elements. And it has to be monotonically decreasing. And then from the previous slide, it is clear that all of the fill-in can only occur in above this envelope. And also due to the orthogonality of the columns of an isometry, all of the non-zero elements above the diagonal will automatically become zero. So this means that we only have to worry about the elements between the envelope and the diagonal. And this quantity we will denote by env. And then this means that the number of eliminations is bounded by this number env. And so an interesting question is to see how can you find the smallest value of env if you allow to perform permutations on the rows and columns of an isometry. So now that we have seen the main method of this talk, we can quickly look at two specializations of this method, which give slightly different bounds. First one is called the fixed envelope method. Here we use a decrement gate, which can be implemented quite efficiently. What it does is simply that it subtracts 1 in the standard basis, meaning that if you look at the matrix, what it does is it moves every row up by 1 position, and the topmost row will be moved to the bottom as depicted here. And so in this method, what we will do is after each householder reflection, which eliminates 1 column, we will perform such a decrement gate. And then we just alternate between these two operations. And what this does is that it makes sure that all of the non-zero elements will be close to the top. And if we then perform this sparse state preparation, we don't have to do this permutation step that I showed to you previously. And this means that we get some savings in CNOTs. In particular, this factor n that we used to have here is now gone. But instead of the number of eliminations, we only have the number of, or the size of the envelope, which gives an improved bound, for instance, for unitaries that allow very small envelopes. And the second method that we can derive from this householder decomposition can avoid all fill-in. The way we do this is by using one clean ancillar qubit. And instead of implementing the original isometry, we will implement an extended isometry, which is essentially the same thing, except that we attach a zero matrix of the same size below this isometry. And then in each case, we can simply do this reduction by reducing each column to a row in this bottom half. And then from the slide about fill-in, you can easily see that there will be no fill-in at all, because here we only have zeros. And yes, we can only simply do these householder reflections and eliminate all of the entries. And this gives a CNOT count that is up to this factor of n again, almost proportional to the number of non-zero elements. And if you recall from the examples that I gave in the beginning, this is kind of what we hope to achieve. So this is a very nice bound. So here we have a summary of the complexities, both of the CNOT gate counts and also the classical complexities. Not going to read them all again, except I'm going to mention that if you have a sparse unitary that is computable, meaning that you can write an efficient function that computes all of the entries. If you give it a row index, for example, you have to efficiently compute all of the entries in that row. Then it is computable, and in that case, you can implement this unitary using only a polynomial number of CNOT gates. And also there's another paper which has used householder transformations to implement dense isometries. And they are focused more on the classical complexity and on performing like a high performance implementation of this decomposition. So let's quickly look at some numerical results for sparse state preparation on n qubits, where we have at most 2 to the s non-zero elements. And here we have, for different values of n and for different values of s, plotted the number of CNOT gates that we get for sparse state preparation. And we compare them to the counts that you get from dense methods. And you can see that we get quite good improvements on these counts. And we also compare them to the upper bounds that we have computed. And again, we get actually much better results than the upper bounds would suggest. So some possible improvements that we could still make are the following. You could, for example, implement better decompositions for permutation gates, because these allow us to, for example, do the reduction of these columns in different orders, which might, for instance, reduce the number of fill-in or the size of the envelope. Also, as I mentioned, these multi-controlled NOT gates can be sometimes implemented up to diagonal, and there do not seem to be any decompositions known for these gates for large values of S. And there are also many combinatorial algorithms in this decomposition, for example, in choosing the order in which you do the decomposition or finding the smallest envelope, which are quite difficult, and there might be still a lot of improvement to be had. So let's just quickly summarize what we did. We presented a method to implement sparse state preparation, which gives improved bounds compared to dense state preparation methods. We demonstrated how the householder reflections allow us to implement general dense isometries, where again we achieve the same near optimal CNOT counts. And for sparse isometries, the same method also gives good synod counts and low fill-in. And then we presented two improved methods, which give slightly different bounds, which we called the fixed envelope method and the no fill-in method. And finally, we showed some numerical results, which show that for sparse state preparation, we indeed get improved synod counts. So if you have any questions, please tell me.
Thank you very much, Emanuel. I see some people are typing, but while they are typing, I'll ask a question, which is, do you know any extensions to this technique that would take into account qubit connectivity when you're building up the circuit?
We have not really thought about that. So.
John Wethering would like to know, what are the use cases of really sparse isometries? Do they appear in algorithms?
Yeah, so unfortunately, so far we haven't found a lot of very interesting sparse isometries, except for the ones that I showed in the beginning as motivation. So we would actually also be interested in hearing from other people if they know of any applications. In the one paper that I cited here, they give some examples. For example, like quantum Turing machines or quantum walks can be represented by these efficiently computable sparse unitaries. And then you can show that quantum circuits can simulate these things efficiently.
Okay, so I think I will give the last question to Stefano Gogioso, who's going to ask, can you do anything like this for approximate state preparations?
I'm not sure, we didn't really think about approximate algorithms, but of course, we only used these householder reflections, which use state preparation and synod gates, or this reflection gate. So if you can do those approximately, then of course you will also get something for sparse state preparation.
Okay, well, I think I'll draw a line under the questions now, since we started late, that we are definitely running into the next talk's time. So thanks very much for the interesting presentation, Emanuel, and I'll see you all in the next session.
Bye.